In this section, we're going to look at rate laws that include multiple reactants. I will note that we've made these problems a little bit harder here than they would be in real life, because we want to make sure that you understand we still have to look at one reactant at a time. As you'll see in the iodine clock lab, we're going to make this easier and more obvious by clearly setting up experiments that only change a single reactant in one set of experiments. Alright, so this gets a lot more complicated when you have multiple reactants. And now the book has a way of doing this with any set of trials, which technically should work, but I find really confusing to explain. There's a simpler way to do this, and it's the way we do it in real experiments, which is you're looking for only one chemical concentration that's changing at a time. So for example, when I look at trials 1 and 2, NO2 minus is not changing. And that's important because I can say any change in the rate must be related to the change in concentration of NH4, right? And since NO2 minus is not changing, it's not important for those two experiments, or it's not important in the difference between those two experiments, I should say. If I wanted to look at NO2 minus, I would look at trials 1 and 3 because only NO2 minus is changing. Now, as I said, I did a lot of kinetics work in grad school and as a postdoctorate. And you would not set up an experiment like this. You would set up 5 or 6 experiments in a row where you're changing only one chemical, and then you would set up 5 or 6 experiments in a row where you're changing the other chemical. So it's really, really obvious what you're trying to do. We don't have time on an exam to give you 12 different experiments. And so as a result, we kind of give you these mixed up experiments where you have to figure out which two trials you want to compare to be important. And that gets confusing. But you just want to kind of really, really slowly break this down and figure out which trials are the best indicator for each experiment. So anyway, we said 1 and 2 is good for NH4. Let's look at those two. So again, we're trying to determine the order of NH4+. So we're looking at trial 2 over trial 1 because NO2 minus is not changing. Again, I'm doing trial 2 here because it's higher. That's going to give us a better ratio. So when I do that, trial 2 over trial 1, rate of trial 2 over trial 1, we get 2 to the y equals 2, where y is a first order reactant. All right, so now look at two trials for NO2 minus. Again, if you don't remember, figure out which two trials have NH4 plus not changing at all, and then use those two trials to figure out the change in rate for NO2 minus. Okay, so I usually do Y here. There's no real great reason for this because I'm just trying to indicate that it's a different compound, therefore a different variable. But you can do X for all three if you want. Just kind of make sure you keep them straight. But our change here was 0.800 molar versus 0.200 molar. And this is 8.60 times the negative fourth over 0.535 times the negative fourth. This really should be 5.35 times the negative fifth. I just wanted to create some numbers that are really, really obvious. And this was the way to do that. But basically we're getting a ratio of 4y equals 16, essentially. We're very close to that. So y is second order. Okay. Now, there's a little bit of noise here. In real experiments, you get a lot of noise, right? So you end up with 4y equals 14 or 4y equals 17. And that's why we do a lot of trials here to figure out these orders. We want to get a ton of information, not just a single trial, but on exams, we can assume those trials are correct. Okay, so now that we know the order of these two reactants, right, what we're going to do is put in concentrations for both chemicals. So we're trying to find the rate constant still. I'm going to pick one trial. I just picked the first one. Plug in our rate, plug in our two concentrations. Now, because the NO2 minus is squared, I have to square both the concentration and the molar. Let me multiply these together. Molar to the 1 times molar squared gives us molar cubed. So we're going to take the rate over that molar cubed number. Now 1 molar and 1 molar on the bottom cross out, and we're left with 2 molars on the bottom. So this becomes 1 over molar squared per second, or molar -2 seconds -1, because we still have the seconds here on the bottom. Again, if you the final answer for this is always going to be putting in the rate law. Rate is equal to 0.669 molar -2 S -1, and then our two chemicals to their order. The last thing I want to mention is that this is our first third order reaction. I know it's third because I'm basically going to add up all of my orders together. This is not important right now, right? But it will be important in next module's discussion of this. So again, first order reactant, second order reactant, add the two together and we get a third order reaction. So go ahead and try this one really quickly. Again, make sure you are only changing one concentration in the two trials you're measuring. And that's a little trickier on this one. Okay, go ahead and pause. I'm going to move to the answer. So, if you're trying to measure N2, we have to look at trials 2 versus trial 3. Those are the only two trials where hydrogen is staying constant, which means we'll get the wrong order for N2. So, in trial 3 over trial 2, again, we always want to use the bigger concentration. We are increasing the concentration by a factor of 3, and we're increasing the rate by a factor of 3. So 3x to the 3 means first order. Now, if we look at H2, we want to look at trials 1 and trials 3 because N2 is staying the same. So again, we are doubling the concentration, so 2 to the y, and we are doubling the rate, so this is also going to be a first order. So we have a rate law where rate is equal to k, N2 to the 1, H2 to the 1. So now that we know the rate law, I'm going to pick any trial. I'll just pick trial 2 at random. I've got the rate. I've got my concentration of N2. I've got my concentration of H2. When I multiply those two molarities together, I'm going to get molarity squared, and then divide molarity per second over molarity squared. Again, that means I'm going to end up with 1 m left on the bottom and seconds on the bottom. So 3.80 m-1 s-1 or 3.80 1 per molar per second.